Hello, and welcome to our video demonstration for Pac-Man, Don't Eat the Ghosts, Teaching AI Ethical Values Through Policy Orchestration. This is joint work between IBM Research and Carnegie Mellon University. In a typical reinforcement learning setup, an agent interacts with an environment. The agent takes an action and the environment sends back a reward and also the updated state that the agent can see. Reinforcement learning has led to many advances in the state-of-the-art of game playing, through the use of reinforcement learning in self-play. This includes TD Gamma and AlphaGo and agents for Dota 2. This is because agents are able to learn creative strategies that humans may not think of. We don't need to tell the agent how to win the game. The agent is able to learn for itself. However, many agents sometimes end up doing something called reward hacking, where it tries to maximize the reward but not necessarily do what we wanted it to, aka finish the game. Problems like these are often studied in the value alignment and machine ethics literature. The idea is that in many settings we want to combine the creativity of reinforcement learning or other optimization techniques with constraints that come from any number of places, including ethics, morals, business process, guidelines, laws, etc. In the machine ethics literature, there's two main approaches that are taken. One is the top-down approach, where we explicitly write down all the rules that we want the machine to follow. The other is the bottoms-up approach, where we show or demonstrate to the agent appropriate actions, and we have him learn how to play within the safe or complies within these constraints. For this demonstration, we instantiate our techniques on the Pac-Man domain. In Pac-Man, we're going to define being moral as not eating the ghosts, but still finishing the game. Our system has two main components. The first is a typical RL framework where the agent plays Pac-Man on its own and learns how to maximize its reward. And this is a typical self-play where the agent just trains on Pac-Man using reinforcement learning. The other is we generate examples of agents playing Pac-Man but not eating the ghosts. We then apply inverse reinforcement learning on these and learn a constrained policy where agents are winning the game but not eating the ghosts. Both of these policies are then put into our agent, which we call the orchestrator here, and we decide which policy to use based on feedback from the environment. In this way, we hope to control the agent's overall behavior by having it act more like the constrained policies or more like the rewarding policies. In our demonstration, we control this trade-off through a parameter called lambda, and by varying the setting of lambda, we can vary the behavior of Pac-Man. In this video, we see Pac-Man playing usually on the reward policy. Here we have lambda set to 0.2, which means that he is almost always taking the action that will maximize the reward. This is demonstrated by him chasing down the ghost repeatedly in order to try to maximize his total points. So here he's chasing after the ghost. And again, Pac-Man chases the ghosts once he has eaten the power pill in order to completely maximize his reward. However, he does know that he can die, so he moves away from the blue ghost when he is vulnerable. By varying lambda, we can see that the constrained policy is more often in effect. Here, once Pac-Man eats the power pill, he stays away from the ghosts, going so far as to run away from them so that he does not end up inadvertently eating them. Now, Pac-Man ends up with a slightly lower score in this setting than the others because eating the ghosts is a rewarding action according to the game. However, because we've varied lambda, we can get Pac-Man to exhibit the behavior that we want, which is not eating the ghosts, because he's following the constraints more often than not. Setting the policy somewhere intermediately by saying, say, lambda equals 0.4, is interesting to see that Pac-Man kind of trades off the two policies. He's aggressive when the power pill has not been eaten, but then as you see, right as soon as he eats the power pill, he switches to the constrained policy and avoids the ghosts. And again, Pac-Man is trying to be as optimizing as possible here when he can be, but then once he observes that the ghosts are scared, he runs away from them instead of eating them. So again, he'll go over here and eat the power pill, and then immediately move to stay away from the ghosts. Note that he does achieve a slightly higher score here because he completes the game faster, which is something that he learned from the reinforcement learning framework. So by varying lambda, we measured the results over 100 games of Pac-Man to see how many ghosts are eaten versus the overall score. We do see a pretty strong cutoff around 0.2 where there's a clear tipping point and Pac-Man sort of knows that he shouldn't eat the ghosts. However, he's still able to get a reasonably high score in this setting. So all in all, our framework is interesting in that we are able to learn a constrained policy through examples and use this to constrain the behavior of an online agent in subsequent actions. Thank you very much.